Hello, everybody. So today we're going to continue talking about NMR, and that's going to be the subject of a couple more lectures because NMR is the most important analytical technique in organic chemistry. Last time we were talking about the various NMR issues, the location of the peak, its chemical shift, and we started talking about the number of signals that a compound will exhibit in its NMR spectrum. And last time we talked about how protons that are in the same environment produce the same signal. And how can protons be in the same environment? One way is if they are related by a symmetry element of the molecule in which they reside. So that's what we were talking about last time. There is a second way in which protons can be equivalent, and that is more subtle, and that is by a rapid mechanism. So we can call this chemical shift equivalence by a rapid mechanism. All right, so by way of introduction to this topic, let's look at chair cyclohexane. All right, so we have our chair, and we have axial protons and equatorial protons. All right, so I would like for you to tell me in the chat, if the chair were frozen in this shape, in other words, if we didn't have the chair-chair interconversion, if the chair were frozen in that shape, in that conformation, how many signals would we be expecting from chair cyclohexane? Right, you're using symmetry. So if cyclohexane were frozen in this chair conformation and the chair-chair interconversion weren't happening, how many signals, how many NMR signals would we be expecting? Give you a big clue, you're using symmetry. So tell me in the chat, how many signals? All right, any takers out there? All right, so we would be expecting 2 signals because the axial, we have axial protons and we have equatorial protons. Every axial proton is related by some symmetry element to some other axial proton. And every equatorial proton is related by some symmetry element to every other equatorial proton. But the axial protons and the equatorial protons are not equivalent to each other by symmetry. And of course they are not, because an axial proton is in a totally different chemical environment from an equatorial proton. An axial proton would be experiencing 1,3 diaxial interactions, whereas an equatorial proton would not. So we are predicting 2 signals from cyclohexane. Okay, so now let's look at a spectrum of cyclohexane and see whether that expectation is confirmed. Okay, so here's the NMR spectrum of cyclohexane, D1, forget about what that, I mean D11, forget about what that means for a second. But we see that at room temp at 0 degrees Celsius, 273 Kelvin, we don't see 2 signals. we see one signal. Well, that's not what we were predicting based on symmetry. We're predicting two signals, but now as you cool the sample down, so here they've gone from 273 Kelvin to 222 Kelvin, as you cool the sample down, now you start seeing the two signals. So we would like to explain what is happening here, and what is happening here is chemical shift equivalence by a rapid mechanism. At 0 degrees Celsius, at 273 Kelvin, the axial protons and the equatorial protons show the same chemical shift, but at lower temperature, the chemical shift between the axial and the equatorial are different, and that's the prediction that we came up with just based on symmetry. So we want to understand what in the world is going on. All right, and what is going on is chemical shift equivalence by a rapid mechanism. All right, so the conclusion here was two signals by symmetry, comma, but get only one signal at 25 degrees C. All right, and so what's going on here is chemical shift equivalence by a rapid mechanism. Okay, and so let's explain what that is. So do you remember way back in Gen Chem, do you remember the Heisenberg uncertainty principle? Well, one of the statements of the Heisenberg uncertainty principle, Heisenberg, I believe it's with an R, Heisenberg uncertainty. One of the statements of Heisenberg uncertainty is that delta E times delta T must be greater than or equal to Planck's constant divided by 2 pi. Okay, so now what does this equation mean? Delta E, that is the uncertainty in the energy. All right, and so that means the ability to measure energy with precision, right? You measure the energy of something, you want to get the same number every time, but ordinarily you don't get the same number every time whenever you measure anything, so that when energy is measured, there's a certain uncertainty, there's a certain spread of values associated with that. All right, and delta T in this equation, this means the lifetime of the state or of the species or whatever it is you're trying, whose energy you're trying to measure. So the uncertainty in the energy times the lifetime of the state, that has to be greater than or equal to Planck's constant divided by 2 pi. All right, that's a statement of the uncertainty principle. Okay, maybe back in Gen Chem, another thing possibly, hope you remember, is the Planck relationship, that E is equal to h nu, where nu is the frequency of the electromagnetic radiation. So now just doing some, it's not calculus, it's not differential calculus, it's something simpler than that. We can rearrange this equation, E is equal to h nu, to read delta E is equal to h, okay, that's a constant, that's never going to change, times delta nu. So the uncertainty of the energy is equal to Planck's constant times the uncertainty in the frequency. We're trying to measure the energy of something. There's going to be a spread of values. There's going to be uncertainty in that, a certain amount of irreproducibility, and that is correlated to the uncertainty and the irreproducibility of the measurement of the frequency. Okay, so now what I'm going to do is I'm going to combine this guy and this guy. And I come up with another statement of the uncertainty principle, which is delta nu times delta t. That must be equal to 1 over 2 pi, right? So I just combined those previous equations and I came up with that. Okay, so now, if we use a 300 megahertz spectrometer, remember the NMR spectrometer has a powerful magnet, and although the units of magnetic field strength that you may have covered when you took this in physics was either the Tesla or the Gauss or something like that, or ESU or whatever, we don't use that in NMR. Instead, what we use is we rate the magnet in units of megahertz, and that's a frequency. So if you use a 300 megahertz NMR instrument, right? And this is the kind of like the basic no frills NMR. The higher the magnetic, the higher the megahertz, the more powerful the magnet. So this 300 megahertz NMR, this is kind of like bargain basement sort of NMR. It's not something super fancy. It is, however, extremely expensive anyway, because an NMR instrument costs approximately $1,000 per megahertz. So even this bargain basement, bottom of the line NMR spectrometer, 300 megahertz, that's still $300,000. So let's say we're using this basic, fundamental kind of low end NMR. And now what we want to do is we want to distinguish. We want to be able to tell the difference between two protons that differ in chemical shift by 0.001 ppm. All right, so now what we're talking about is the resolution of an NMR instrument, right? Every scientific instrument has a resolution, and about the limit of an NMR resolution is about 1,000th of a ppm. So like, for example, on your cell phone, right, that camera has a resolution. If you're trying to take a picture of something that is less than 1 pixel, it's either going to be blurred or it's not going to come out at all. So every scientific instrument has a resolution, and that's about the limit of resolution of an NMR. If you have one proton over here and another proton over here, and their chemical shift difference is 0.0000001, the NMR is not going to be able to tell the difference between those two protons because the resolution of the instrument is about 1,000th of a ppm. So this is just realistic. So if we want to be able to tell the difference between two protons that differ in chemical shift by 1,000th of a ppm, oh, and by the way, one ppm, remember that means parts per million. Part per million of what? Part per million of the rating of the magnet in units of megahertz. So 1 ppm is equal to 300 hertz. And so the resolution that we're going for, this difference of 1,000th of a ppm, that is equal to 0.3 hertz. Okay, so we're trying to tell the difference between these two protons. And so this uncertainty in the frequency, that's the delta nu in that equation that we previously came up with, which is this. Okay. Oh, which is this up here, right? The delta T. Okay, so now let's plug all of these numbers into this uncertainty relationship, and we see that 0.3 hertz, that's the same as a per second, right? Remember that a hertz is a frequency that is per second. So that's delta nu, 0.3 per second, times delta T, that's the lifetime of the state, must be greater than or equal to 1 over 2 pi. And so now when I rearrange this equation and plug in values of 2 pi, what I get is delta T, the lifetime of the state, how long a state must exist, must be greater than or equal to about half a second. So this is why at 25 degrees C, cyclohexane gives us only one peak, because we know that the cyclohexane is going from one chair to another chair hundreds of thousands of times per second. The lifetime of one chair is much, much less than delta T, equal 0.5 seconds. So this is telling us that for us to be able, at the very limit of resolution, with the bottom of the line spectrometer, the state has to live for greater than half a second. But chair cyclohexane isn't living for half a second. It's living for much, much less than that. Okay, so we have, going back here to chair cyclohexane, and we have a proton, let's call him HA, he's axial. We have another proton, HB, let's call, he's equatorial. And this is undergoing a chair flip. And when the flip happens, every upward pointing carbon becomes downward pointing, and every downward pointing carbon becomes upward pointing, and every axial proton becomes equatorial, and every equatorial proton becomes axial. So as the chair, and how long does this take? Well, the activation energy for this process is about 45 kilojoules per mole. When we plug that into the Eyring equation, we see that the rate constant for this process is 8.0 times 10 to the 4th per second, meaning that the lifetime of the state, delta T, the lifetime of each chair works out to be 12 microseconds. Oh, that is way below the half a second that we need to be able to distinguish two protons that are very close in their chemical shift. So the reason that chair cyclohexane gives us only one peak at room temperature is because the NMR instrument can't tell the difference between an axial proton and an equatorial proton at that temperature, because an axial proton is axial for only 12 microseconds, and it needs to be axial for half a second in order for the NMR instrument to be able to tell the difference between axial and equatorial. That's the result of that's what the Heisenberg uncertainty is telling us. Okay, so let's look at some more pictures here. Okay, so as we decrease the temperature of the sample, now the NMR can tell the difference between an axial proton and an equatorial proton, because the lifetime of the chair is increasing, and now it is approaching that half a second lifetime that's required. Okay, so on this slide here, what I have is at 203 Kelvin, at 295 Kelvin, we see one peak, but when we lower the temperature down to about 203 Kelvin, the interconversion is much slower. So at this, so because of Heisenberg uncertainty, what the NMR sees is not at room temperature, where the lifetime of the state is less than the half a second that's required. What we see is an averaged signal, right? We don't see axial and we don't see equatorial. What we see is the average of where the equatorial chemical shift is and where the axial chemical shift is. And so the analogy that is always given here would be like looking at the blades of a fan. Because the fan is spinning around so fast, we don't see the individual blades. A fly could, but not a human being. We don't see the individual blades. We just see something that is the average of the position of the blades as they undergo this rotation in the fan. All right, so that is chemical shift equivalence by a rapid mechanism. Cyclohexane gives us one peak, not because all of the protons are equivalent to each other by symmetry, but because all of the protons are equivalent to each other by a rapid mechanism. The NMR instrument, because of its slow time scale, cannot tell the difference between an axial proton and an equatorial proton at a high temperature. All right, so there are more consequences to this rapid mechanism than with the chair. And so let me give you the executive statement about the rapid mechanism, and then we'll unpack it. All right, so first proposition here is that the 3 protons of a methyl group are always equivalent, either by symmetry or by a rapid mechanism. So if you see a molecule that has a methyl group in it, that's going to give one signal always. All right, the second proposition here is that the 2 protons of a methylene group, of a CH2 group, are equivalent unless ... there's a chirality center somewhere in the molecule. So the 2 protons of a CH2 group, they're always going to give you one peak, but not because of symmetry, but because of a rapid mechanism. Unless there's a chirality center somewhere in the molecule, and then those 2 protons are going to be then those 2 protons are not going to be equivalent, and they're going to give you 2 different signals. Okay, but now the truth is so messy, right? We have to put a big asterisk here because there is an exception that we have to pay attention to. And that is that symmetry supersedes, do I dare use the word, symmetry trumps the rapid mechanism. So we want to look at symmetry first. And if the molecule is rigid, if some kind of molecular motion is not possible, if it's not a chair, if it's not undergoing some kind of rapid rotation or some kind of rapid process, then symmetry overrules these considerations. Okay, and we'll talk about an example of that in a while. Okay, So the 3 protons of a methyl group are always equivalent. Let's look at how we come up with that. And this is an application of the rapid mechanism. All right, so let's imagine this situation here. We know that chairs interconvert, but we also know that the Newman projection undergoes rotation. So here's a Newman projection, and what I'm going to do is I'm going to label label the carbon in the back like that. Notice the carbon in the back isn't a chirality center, and I'm going to put 3 protons up here in the front. That's going to be my methyl group. And I'm going to label this proton HA. I'm going to label this proton HB, and I'm going to label this proton HC. Okay, so look at this guy. If this Newman projection were frozen in this conformation, in other words, if that single bond did not rotate, how many signals would the methyl group give me, right? I'm not looking at this proton back here. I'm just looking at the 3 protons of this methyl group right now. So if the Newman projection were frozen like this, how many signals from that methyl group? Oh, it is going to give me 2 signals because this Newman projection has symmetry, right? There's a plane of symmetry that says that the left is the mirror image of the right. So in this Newman projection, the HC is equivalent to the HB, but the HA is unique. Okay, so this is going to give me 2 signals, and it's going to give me 2 different chemical shifts. So I'm going to call the chemical shift of HA, I'm going to call him delta 1. That's his chemical shift. And delta C has the chemical shift of delta 2, and the chemical shift of HB is also delta 2. They're equivalent by symmetry. But we know that the carbon-carbon single bond rotates, right? And very fast, billions of times per second at room temperature. So we look in on this Newman projection a billionth of a second later, and what has happened here is now HC has come up here to 12 o'clock, HA is down here at 4 o'clock, and HB is over here at 8 o'clock. Okay, and again, this conformation would once again give us 2 signals. The HB and the HA are equivalent to each other, but the HC is unique. And so the HB, so if I were to remove all of the A's and B's and C's, this Newman projection will look just like that one. So that I hope it is clear that the HB here would have chemical shift delta 2, HA would have chemical shift delta 2, and HC would now have chemical shift delta 1. Okay, so now finally, let's look in on this Newman projection one last time, a billionth of a second later. And let's see what has happened here. Is now HB is up here at 12 o'clock, HC is down here, and HA is at 8 o'clock. And once again, we're expecting 2 signals. The HA is symmetry equivalent to the HC, and HA has chemical shift delta 2. HC has chemical shift delta 2, and HB has chemical shift delta 1. Okay, so that's the analysis of the chemical shifts. Now let's collect results. For the HA, is that sometimes HA has chemical shift delta 1. So I'm just going to illustrate it this way. I'm going to say, okay, so here's chemical shift delta 1. Sometimes HA has chemical shift delta 1. And sometimes HA has chemical shift delta 2. Oh, it has it twice, right? So here's delta 2, and it's going to have that chemical shift twice, right? So I'm going to make that line twice as long. But HA is going from delta 1, chemical shift delta 1 to chemical shift delta 2 and back again billions of times per second. It has to, in order for the NMR instrument to tell the difference between delta 1 and delta 2, HA has to be delta 1 or delta 2 for at least half a second. Right, we just went through that. But HA is going from delta 1 to delta 2 billions of times per second. It's what the NMR sees is an average of these two signals. Okay, so I'm going to illustrate it this way. I'm going to draw a peak, and the average, since HA is delta 2 twice, the average is going to lie closer to delta 2 than to delta 1. So I'm just going to illustrate the peak like this. All right, so that's what the NMR would see. It's going to see a peak, and that peak is the time average of delta 1 and delta 2. It's closer to delta 2 because HA has delta 2 more times than it has delta 1. Okay. So much for HA. Now let's look at HB. Okay, HB sometimes has delta 1 and it sometimes has delta 2. Oh, but HB has delta 2 twice. So I'm going to make that line over here twice as long. And once again, what the NMR sees is the average of these two signals. Oh, it's exactly the same result that I got for HA. All right, and so now let's see what is HC doing. HC has chemical shift delta 1, and it has chemical shift delta 2, but it has chemical shift delta 2 twice. So I'm going to make that line twice as long, and it's shifting between between delta 1 and delta 2 billions of times per second. That's way beyond the NMR's ability to detect the difference between delta 1 and delta 2, and so we get the average. Well, so what we've just shown by this analysis is that the 3 protons of a CH3 group are equivalent by a rapid mechanism. They could be equivalent by symmetry in some very simple molecules, but in general, they're going to be equivalent by a rapid mechanism. These patterns are all the very same, exact same thing. The 3 protons of a CH3 are equivalent by a rapid mechanism. They're going to give you one peak. Okay, so that is the explanation of proposition number 1 that we had there. Okay, so now let's look at our next proposition, and that is going to be the equivalence of the 2 protons of a CH2 group. All right, so that means more Newman projections. So, whoa. It's not how you draw Newman. So now I'm going to go to another molecule, and I'm going to call this guy HA, and I'm going to call this guy HB. And if the Newman were frozen in this conformation, HA and HB are related by symmetry, they're going to have the same chemical shift. I'm going to call that chemical shift delta 1, and HB has that same chemical shift delta 1. All right, now let's look in on this Newman projection a billionth of a second later. Let's see what's happening there. Okay, so now a billionth of a second later, the bromine has shifted down here to 4 o'clock. The HA has come up here to 12 o'clock, and the HB is over here now at 8 o'clock. All right, now the symmetry has been broken. HA and HB are no longer related by any kind of symmetry element. So that here we saw that HA was equivalent to HB, but now here HA is not equivalent to HB. They're in totally different chemical environments. They are no longer related by symmetry. Furthermore, the 8 o'clock proton in this Newman projection does not have the same chemical shift as the 8 o'clock proton in this Newman projection, because this proton is now in a different environment than this proton. So this is a new chemical shift, delta 2. So when a proton, a proton is at 8 o'clock over here, the bromine is sandwiched in between the two chlorines. When the proton is at 8 o'clock in this Newman projection, the bromine isn't sandwiched between those two protons any longer. This proton is in a different chemical environment. It's distinguishable from this proton. So even though the proton is still at 8 o'clock in both of these Newman projections, it's not the same chemical environment. We could tell the difference between these two. And HA, that's a new chemical shift. I'm going to call him delta 3. Okay, so now let's look in on this Newman projection a billionth of a second later. And now the bromine has shifted over here to 8 o'clock. HB is up here at 12 o'clock, and HA is down here at 4 o'clock. Okay, and once again, we see there is no symmetry element that relates HA to HB, so these two protons are not equivalent to each other. All right, and what about their chemical shifts? Well, what we notice here is if we were to remove the labels, the A and the B and the C, these two guys are enantiomers. These are enantiomers. And one of the things that we know about enantiomers is that enantiomers have the same properties unless they are interacting with other chiral substances. But these guys aren't interacting with any other chiral substance. Right, we're just looking at a sample of this molecule. So that this guy here, HA, over here, has the same chemical shift as delta 2, and this guy up here has the same chemical shift as delta 3. Okay, well, did I do something wrong here? Is my labeling wrong? No. Okay, so that's the analysis. Now let's collect results like we did before. Okay, the HA. Sometimes the HA has chemical shift delta 1. All right, sometimes HA has the chemical shift delta 2. And sometimes HA has the chemical shift delta 3. But it's going between 1, 2, and 3 billions of times per second. The NMR just sees an average of all of these signals. So just accidentally, I've equally spaced these lines. So, but the difference between delta 1 and delta 2 and delta 3, that could be anything. But just the way I've set this up, I'm just going to draw the signal average here, somewhere there in the middle. Okay, so sometimes HA is delta 1, sometimes it's delta 2, sometimes it's delta 3. All right, now let's look at the HB. Is HB ever delta 1? Yeah, it is. Is HB ever delta 2? Yeah, it is. Is HB ever delta 3? Yep, it is. And the NMR sees the signal average. It's exactly the same pattern. HB and HA have exactly the same pattern, exactly the same result. So that the two protons of a CH2 group are chemical shift equivalent, not by symmetry, but by a rapid mechanism. They're going from one chemical shift to another chemical shift to another chemical shift billions of times per second. The NMR can't keep up with that because that would be a violation of Heisenberg uncertainty. The two protons of a CH2 group are equivalent unless ... So that's the third situation that we have to consider. And that is they are equivalent unless there's a chirality center somewhere in the molecule. So let's look at our three Newman projections once again. But this time, let's look at a situation where a chirality center is present. So my CH2 group, I'm going to put him up here. And now that carbon in the back, I'm going to make that a chirality center. Cl there, Br there, and H there. So now I have a chirality center. So now in this Newman projection, the HA and the HB are not equivalent to each other. There's no symmetry operation that relates these two. So this is a chemical shift. I'm going to call him delta 1. And HB here has a different chemical shift. I'm going to call him delta 2. Okay, and so now let's draw the rest of these Newmans and analyze the chemical shift. I'm leaving that chirality center in the back alone, and I'm diddling with the CH2 group, the methylene group in the front. And so this is now HA and this is now HB. And once again, we see that HA is not equivalent to HB because there's no symmetry element that relates them. And furthermore, just like we saw before, we see that this that when a proton is at 8 o'clock in this conformation, it does not have the same chemical shift as when a proton is at 8 o'clock in this conformation, because now we have this is a different chemical environment, and these two conformations would be distinguishable. See, you see here how we have a proton that is sandwiched between Cl and Br, whereas we don't over here. So the 8 o'clock proton here is different from the 8 o'clock proton here. We could tell the difference if the Newman projection were frozen there. So this is a new chemical shift, delta 3. And this is a new chemical shift that we haven't seen before, delta 4. Okay, last Newman projection. So HA is down here at 4 o'clock, HB is up here, and we have our chirality center in the back there. And once again, we see that HA is not equivalent to HB. And another thing we notice is that this 8 o'clock proton, this 4 o'clock proton over here, that is a new chemical shift. Let's call him delta 5. And this is a new chemical shift up here, delta 6. See, in the previous examples, we saw that sometimes the HA and the HB were equivalent. Here, they're never equivalent. So we're getting the inkling of the idea that the two protons of a CH2 group are never equivalent to each other when there is a chirality center present in the molecule. Okay, so now let's collect results. HA, sometimes he's delta 1. Is he ever delta 2? No, he's never delta 2. Is HA ever delta 3? Is HA ever delta 3? No, he's never delta 3. Is HA ever delta 4? Yes, he is. So let's see, I'm going to put 1. So sometimes HA has delta 4. Is HA ever delta 5? He is. It's supposed to be a delta 5. Is HA ever delta 6? No, he's never delta 6. Okay, now let's look at HB. Is HB ever delta 1? Nope. Is HB ever delta 2? Yep. Is HB ever delta 3? Yep. Is HB ever delta 4? Nope. Is HB ever delta 5? Nope. Is HB ever delta 6? He is. But again, we're going from one set to another set. I mean, from one chemical shift to another chemical shift, billions of times per second. All the NMR can see is the average. So these three guys are going to average out maybe to something here. These three guys are going to average out to something totally different, maybe something like that over there. So these two, even the averages are going to be different. So what this analysis is telling us, that the two protons of a CH2 group are equivalent unless ... there's a chirality center somewhere. It doesn't have to be next door, somewhere in the molecule. All right, so that is chemical shift equivalence by a rapid mechanism. All right, now, and I said that the symmetry in a rigid molecule is of the more important consideration, because all this explanation that I just went through, that is predicated, it is based on the ability of the molecule to undergo rotation. But let's look at an example where the two protons of two protons of a CH2 group would be equivalent, even if would be non-equivalent, even if there's a chirality center. So that could be something like this. Let's see. Is there a chirality center in this molecule? No, there's not, right? There's no chirality center. So if this is all we remember, the two protons of a CH2 group are equivalent unless there's a chirality center, then we would come up with the mistaken, with the wrong conclusion that this proton, right, no chirality center, no chirality center in this molecule. And so we would come up with the incorrect conclusion that HA is equivalent to HB. Question? Oh, of course they're not, because the symmetry consideration in this rigid molecule where rotation is not allowed, and we just went through an explanation that was based on the rapid rotation of single bonds, the HA and the HB here are not equivalent to each other. The HA and the HB aren't equivalent to each other because the HA is cis to a Cl and the HB is trans to a Cl. They're in totally different chemical environments. So this is an example of where symmetry is more important than the rapid mechanism. Why? Because a rapid mechanism does not operate in this molecule. There is no rotation of a single bond that puts A where B is and that puts B where A is. The molecule is rigid. Okay, so, it's time for my break to go have some coffee. So I'm going to leave you with a problem. I'm going to leave you with a problem here for you to work on while I'm gone. Let's see, where's my problem? Hope it's here somewhere. Uh-oh. Oh, shoot. Where'd you go? Okay, well, can't find it in my slides there. I don't know where it is. I'll just write it out here for you. Stop this. How many signals? Right, so here in this molecule, tell me how many signals I'm going to get. All right, so my computer is saying 9:52. I'll be back at 10 o'clock. Did you work on this problem while I was gone? Tell me in the chat how many signals. So how many signals is this molecule going to give? Anyone want to give it a shot? Six signals. This guy here, he's a chirality center. And a chirality center makes the two protons of a CH2 group non-equivalent. So this proton here, HA, he's different from this proton there. We have a proton here, HC. Here's a CH2 group. This proton here is not equivalent to this proton here. And then the three protons of a methyl group are always equivalent to each other. So we have a total of 6 signals. Okay, now we have to pile on the complications as if this weren't already complicated enough. But what we need to talk about is accidental equivalence. And this happens. This is just something that we have to be aware of. And this is not something that you can look at the structure of the molecule and predict the accidental equivalence. But sometimes the chemical shifts of two protons that are not equivalent in principle are so close together, you know, that 0.000001 ppm, that even though they're not supposed to be equivalent, they are equivalent to each other. So this accidental equivalence happens when the chemical shift difference of two protons, of two, let's say, non-equivalent protons, of two non-equivalent in theory protons is less than about 0.001 ppm. So that's the limit of resolution of the spectrometer. So this is just something that we have to be aware of, that protons sometimes that are not supposed to be equivalent are equivalent anyway. All right, so let's look at some spectra, and let's look at some nice clean examples and then some examples that aren't as clean. Okay, hope they're here somewhere. All right. So here's an example of a molecule. I see a chirality center over there at 3 o'clock. And down here, I see HA and HB. Those are, that's a CH2 group. That chirality center, notice the chirality center doesn't have to be next to the protons under observation, just has to be somewhere in the molecule. And what we see here is that the HA and the HB give this pair of beautifully separated signals here. So here, this is a very nice demonstration of how the two protons are not chemical shift equivalent. But if you look at a molecule, this next example here, see there's a chirality center. So this is 1,3-dichlorobutane. Carbon 3 is a chirality center. So I'm supposed to get 1, 2, 3, 4, 5, 6 signals, but I don't see 6 signals. I only see 4 signals. So this envelope here, that's 1 signal. This envelope here is another signal. There's another one, 3. I see 4 signals. Why is it? Why is that? Because the protons at carbon 1 and the protons at carbon 2, Their chemical shift difference, even though they are in theory not equivalent to each other because of that chirality center, their chemical shift difference is very, very small. It's below the detection limit, the resolution limit of the spectrometer. So this isn't something that we can anticipate. This is something we should just be aware of, but it's not something that we can predict just by looking at the spectrum. Okay, so now this spectrum here is a nice entree to discuss the next NMR issue, which is the splitting of these peaks. So we see 4 signals, but some of them are split into 2 components, 1 into 4, 1 into 3, and 1 into a lot. So the next issue to talk about is splitting. And this is the most informative aspect of NMR spectrometry. It's also the most difficult one. So let's talk about signal splitting. Okay, when to expect splitting. We have two kinds of splitting. We have the so-called 2-bond splitting. Sorry, I'm hung up here. Okay, when to expect splitting. We have so-called, we have 2-bond splitting and we have 3-bond splitting. So if we have a proton that is 2 bonds away from another proton, and all important here, right? This is called 2-bond, or it's also called geminal splitting. When a proton is 2 bonds away from another proton, and all important, these protons are not equivalent to each other. That's when we can expect splitting. The other situation in which we can expect splitting is 3-bond or vicinal splitting, where you have a proton that is 3 bonds away from another proton, and all important here, these protons aren't equivalent to each other. So this is called 3-bond splitting, or it's also called vicinal splitting. There is longer range splitting, where you have 2 protons that aren't equivalent to each other, that are farther away than 3 bonds. But in that case, either the splitting is very small or it's 0. So in general, we don't expect splitting there, but we do see it. There's also longer range splitting, but let's confine ourselves to 2-bond and to 3-bond splitting. So when 2 protons are 2 bonds away or 3 bonds away from another proton, and those protons are not equivalent to each other. Protons that are equivalent to each other do not split each other. Okay, the physical basis of splitting is, once again, let's look at our little simple-minded picture of the spectrometer with that bar magnet that we've seen many times before. So here we have our external laboratory magnet, the lines of force emanating from the North Pole to the South Pole. All right, and let's just talk about 3-bond splitting. So here we have a proton, and I'm going to call him the observed proton. So that's the proton whose splitting we're trying to understand, and I'm going to put him 3 bonds away from another proton that I'm just going to call HA, right? We're looking at the observed proton. Now remember that the whole basis of NMR is that the observed proton is spin up, right? It's aligned with the field, and it absorbs radiation, and it's promoted to the higher energy spin down state. But HA over here, he's not the proton under observation. So he could be either spin up or he could be spin down, right? We're not trying to understand the splitting pattern of HA. We're trying to understand the splitting pattern of H observed. So the H observed, so HA could be either spin up or spin down. Okay, and so we talked about an equation before, which is that the delta E, right, the energy gap between the spin up state and the spin down state, that is equal to H times the magnetic field experienced by the proton. But now here we reveal that a spin up proton and the spin down proton produce a tiny little magnetic field of its own. So how many magnetic fields is that now, right? So the HA proton is creating a little tiny magnetic field of its own that is aligned when it's spin up with the external field, and that is aligned against the field when it is spin down. Okay, so this leads to some more equation here. The field experienced by the proton in this situation will be B lab, the external field, minus the BE, that's the magnetic field that is caused by electrons. And in this case, the external field is being aided and abetted by the magnetic field of the neighboring spin up proton. So that's going to be a plus B sub S, right? That's the magnetic field. This is the magnetic field of the neighbor spin up. In this situation, delta E is going to equal to all of the very same, it's going to equal to all of the very same thing, B lab minus BE, but now the magnetic field is being detracted from by the neighboring proton, which is spin down. So collecting these equations, we see that delta E is equal to H B lab minus BE plus or minus BS. And so the signal of H observed is going to be split into two components because of the magnetic field of the neighbor non-equivalent proton 3 bonds away. So what we see is two peaks, one of them corresponding to the energy of one of the states and the other one corresponding to the energy of the other state. So we're going to see these two peaks, and these two peaks are separated by what is called the coupling constant, J, right? J, this is the coupling constant. And the coupling constant is given in units of Hertz. Okay, so this is the physical basis of splitting, is that the peak of the observed proton is split into a bunch of components because of the magnetic field of the neighboring proton. Yeah, and the distance between these two peaks is J. Okay. So now we can talk about, now we understand where splitting comes from, and now we introduce we know when to expect splitting, and now we can introduce the very important N+1 rule of splitting. The N+1 rule. The N+1 rule. N+1 rule splitting. Okay, so this is a lot. So let H observed be the observed proton. All right, this is the proton whose splitting pattern we're trying to understand. If the H observed is 2 or 3 bonds from N other protons, right? So 2 or 3 bonds from 5 other protons or 6 other protons or 3 other protons or whatever. If the H observed is 2 or 3 bonds from N other protons, and H observed is not equivalent to the N other protons, because remember, we only see splitting when between protons that aren't equivalent to each other, either in theory or in principle or by accident. If the H observed isn't equivalent to the N other protons, but the N other protons are all equivalent to each other, comma, then the signal of H observed is split into N plus 1 components. Okay, that's a lot, right? This is a very important rule that helps us understand what that NMR signal is going to look like and what degree of splitting it's going to exhibit. So the observed proton is 2 or 3 bonds away from N other protons. The observed proton isn't equivalent to those N other protons, but those N other protons are all equivalent to each other. Okay, so we can have we can introduce some important vocabulary here. Let's say when N is equal to 0, in other words, the observed proton doesn't have any other proton with which it is not equivalent, either 2 or 3 bonds away. N plus 1 is equal to 1. And the signal from H observed signal is unsplit, right? It's just one majestic line. This is called a singlet, and it has the standard abbreviation S. And what does a singlet look like? It's just, an unsplit signal. It's just a peak. All right, let's keep going. When N is equal to 1, N plus 1 is equal to 2. That signal is called a doublet, standard abbreviation D. And what a doublet looks like is 2 lines of more or less equal height, 1-to-1. 1-to-1 height separated by that coupling constant. Let's keep going. When N equals 2, N plus 1 is equal to 3. That's called a triplet, standard abbreviation T. And a triplet is a 1-to-2-to-1 pattern of lines like that. See, so a triplet is 3 components, but it's not 3 components of the same size. The middle line is twice as big as the outer lines. Okay, keep going. When N is equal to 3, N plus 1 equals 4. That's called a quartet, standard abbreviation Q. And what does a quartet look like? It's 4 components, but it's not 4 components of equal height. It's a 1 to 3 to 3 to 1 pattern like that. A 1 to 3 to 3 to 1 pattern like that. And then we could keep going, 4, 5, da, 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 da. So after this, there would be called like a quintet or a hex or a sextet or a septet, and so on and so forth. Okay, so let's look at this spectrum once again. And we can see the splitting here. Is that this guy, that's what a doublet looks like. That's a quartet, a 1 to 3 to 3 to 1. And this is a triplet, a 1 to 3 to 1. And this is a sextet. It has six components. And notice how the middle lines of these multiplets are bigger than the outer lines. All right, so now we want to explain how we're getting these intensity ratios. And in order to do that, what we need to drag in is the Pascal's triangle. So do you know about Pascal? Pascal, he was a triangle. The Pascal, he was a French philosopher in the 1600s, and he came up with the binomial theorem. He's also a philosopher. And the Pascal's triangle is a figure, all of whose sides are 1. And then the interior numbers are the sum of the supervening numbers. 1 plus 1 is 2. Next line. 1 plus 2 is 3. Next line, 1, 4, 6, 4, 1. Next line, 1, 5, 10, 10, 5, 1. And we could keep going, right? This is the Pascal's triangle. And the importance of this for NMR is that this first line of the Pascal's triangle, this is what happens when n equals 0. It's a singlet. Okay, this next line is giving us the intensity pattern when n equals 1. 1 plus 1 is 2. That's what a doublet looks like. It's 2 components of about the same height. Okay, next line. N equals 2. That's the triplet. It's a 1 to 2 to 1. It's 3 components. The middle line is twice as big as the outer lines, and so on and so forth. N equals 3. That's a quartet. It's a 1 to 3 to 3 to 1. Next line. N equals 4. That's the so-called quintet. It's going to be 5 lines, but it's going to be 1 to 4 to 6 to 4 to 1. So each of these multiplets, these splitting multiplets, kind of like a little pyramid where the interior lines are going to be bigger than the outer lines. Okay, so we can use this Pascal's triangle to predict what the shape of the NMR multiplet is going to look like. So why does the Pascal's triangle work? Let's talk about that. So here is the observed proton, and I'm going to put the observed proton 2 bonds away from proton HA and make a little what is called character table. All right, the observed proton, he has to be spin up, right? Because it's only the spin up protons that can absorb the RF radiation and be promoted to the higher energy spin down state. So I could put in here an upward pointing arrow, but it's just more efficient here to use the quantum mechanical designation plus 1/2, right? This means spin up. The observed proton has to be spin up, but the neighboring proton, HA, he can be either spin up or spin down. So he can be plus 1/2, spin up, or he can be minus 1/2, spin down. The sum of these microstates, this plus this, adds up to 1. The sum of these microstates add up to 0. And so this is what is going to give us this pattern of the doublet. All right, so now let's make this character table for another situation. That will be the observed proton. And this time I'm going to put the observed proton 3 bonds away from two other protons. Let's call this guy HA and HB. But in this situation, let HA equal HB, right? I'm just putting these labels on these protons just to keep track of them. Okay, so here's a situation where we can expect splitting. The observed proton is 3 bonds away from 2 other protons, n equals 2. And the n other protons are all equivalent to each other. Okay, so we can make this little character table once again. The observed proton, he always has to be spin up, plus 1. But HA could be either spin up or spin down. And HB, he could be either spin up or spin down. So there's that's one possibility. Everything is spin up. Okay, next possibility could be the observed proton has to be spin up. HA is spin up, but HB could be either spin up or spin down. So there's another set of possibilities. Another possibility could be that the HA could be spin down where the HB is spin up. That's another set of possibilities. And the final possibility is that H observed is spin up, but the neighboring protons are spin down. So those are all of the spin microstates that we could get from this situation. The sum is going to be, this adds up to plus 3/2. This guy adds up to plus 1/2. This guy also adds up to plus 1/2. And this guy adds up to minus 1/2. And so what we see is that this guy happened twice. So that this magnetic microstate, he's twice as likely as either the one on the top or the one on the bottom. And this is going to give us our triplet. This is going to give us our triplet with the 1 to 2 to 1 intensity pattern. That's going to be the triplet. There's one state, and then we have another state that's twice as likely, and then we have a third state. And so that's our 1 to 2 to 1 triplet. And we could keep going. We don't have time to do so, but we could keep going with this character table and see what happens when the observed proton is 2 or 3 bonds away from 3 other protons. We would do the same analysis, and we would come up with that 1 to 4 to that 1 to 3 to 3 to 1 intensity pattern, because 2 of those microstates would be repeated 3 times. So that's why this Pascal triangle works, and here's the explanation for that. Okay, so that's all very well and good. How about let's get into let's get to a type of problem that let's just try to predict some splitting patterns and then do a more complicated problem. All right, so something like this. So tell me, how many signals? Tell me in the chat. let's look at this molecule. And first of all, let's see how many signals are we going to get. Can I go back to this page for a second? That's this one. Does someone want that again? Okay, well. So how many signals are we getting from this guy? 3 signals, right? This proton here, call him HA. There are 2 protons here. They are equivalent to each other because I don't see any chirality centers here. The 2 protons of a CH2 group are equivalent to each other unless there's a chirality center somewhere in the molecule. And then there's a methyl group back over here. And the 3 protons of a methyl group are always equivalent to each other. So this is going to be 3 signals. Okay, now let's talk about the splitting. Remember, we're talking about N+1 rule, splitting. And what does that N mean? That N doesn't mean the number of protons in the set. So here there's only one, there's one HA, but N does not equal 1. There are 2 HBs, but N does not equal 2. There are 3 HCs, but N does not equal 3. So let's just get that. Out of the way right away. N stands for the number of non-equivalent neighbors. So if you want to think of N as standing for neighbors, that usually works. Okay, so for the HA, what is the value of N in the N+1 rule? Yeah, tell me in the chat, what is N for the HA? It's not 1. How many neighbors? That's what N stands for. How many neighbors 2 bonds or 3 bonds away that are not equivalent to the HA? Yeah, there's 0. Let's take a little trip. Let's go 2 bonds. From HA, 2 bonds. That's not a hydrogen. That's not a hydrogen. So there's no 2 bond splitting. What about 3 bond splitting? Let's take a little trip. From HA, let's go 3 bonds. We hit a carbon. That's not a hydrogen. So for HA, N is equal to 0. N+1 is equal to 1. It's a singlet. So how'd that go? Let's try this for the HB, right? What is N for the HB? How many non-equivalent neighbors, 2 bonds or 3 bonds away? What is N for the HB? N for the HB is 3. So for this set, N is equal to 3. Okay, so let's take a little trip. 2 bonds away. Oh, if I go 2 bonds away from HB, I hit another HB, and equivalent protons don't split each other. So there is no 2 bond splitting. Let's take a little trip 3 bonds away. 1, 2, 3. We hit a carbon. That's not a hydrogen. Let's go the other way. 1, 2, 3. Ding, ding, ding. HB is 3 bonds away from an HC, and the HB are not equivalent to the HC, so there's going to be splitting. But the HB, both of them are 3 bonds away from 3 HC protons. So N equals 3. N+1 equals 4. That's a quartet. It's a 1 to 3 to 3 to 1 quartet. So that's what's the splitting of the HB. All right, so now let's try it for the HC. What is N? What is the value of N for the HC? It's not 3. The value for N for the HC is 2. N plus 1 is equal to 3. That's going to be a 1 to 2 to 1 triplet. Okay, so let's take a little trip from HC, 2 bonds away. We hit another HC. Protons that are equivalent to each other do not split each other. So each of these HC is 2 bonds away from another HC. There's no splitting. Let's take a trip 3 bonds away. 1, 2, 3. Oh, we hit an oxygen. That's not a hydrogen. Try again. 1, 2, 3. 1, 2, 3. Yeah, when we go 3 bonds away from HC, we hit 2 HB protons. And the HB are not equivalent to the HC, but the HB are all equivalent to each other. So that we have 3 bonds splitting, N equals 2, N plus 1 equals 3. It's a triplet. So how's that going? N stands for neighbors. You can think of it that way. Okay, let's try again. What about something like... something like that. How many signals? Tell me in the chat. How many signals? Three signals. We have the HA. Oh, here's a CH2 group, but I don't see any chirality centers in the molecule, so those HB are equivalent to each other. And there's another CH2 group, no chirality centers. Those protons are equivalent to each other as well. So we're going to have 3 signals. What's the splitting pattern of the HA? I need a word that ends in at. I need a word that ends in at. What is the splitting pattern of the HA? I want a word that ends in at. It's a singlet, right? Because for the HA, N is equal to 0, N plus 1 equals 1. The HA are 2 bonds away from another HA. There is no splitting there. The HA is 3 bonds away from a carbon. 1, 2, 3 from an oxygen. 1, 2, 3. N equals 1. That's a singlet. What's the splitting pattern of the HB? I need a word that ends in at. This is going to be a triplet. N is equal to 2. The HB are 3 bonds away from 2 HC protons. N plus 1 is equal to 3. That's a 1 to 2 to 1 triplet. What about the HC? What is the splitting pattern of the HC? I need a word that ends in at. Oh, that's going to be another triplet, right? N is equal to 2. N plus 1 equals 3. That's a 1 to 3, a 1 to 2 to 1 triplet. Okay, so I hope you're getting comfortable with predicting the splitting pattern. Remember that the N stands for the number of neighbors, right? All right, so now let's do a different style of problem. Our goal in NMR spectroscopy is to go from a spectrum to a structure, but we are not quite ready for that yet. So let's do this other kind of problem where we are sketching what we think the NMR spectrum is going to look like. Okay, so sketch the NMR of, let's see, sketch the NMR of this guy here. Okay, so this is a step. Let's go through the step-by-step of this. Okay, first of all, how many signals? All right, we want to sketch the NMR. This is not our goal in our study of NMR. We want to go from a spectrum to a structure, but here we're going to go from the structure to the spectrum. How many signals? There are going to be 5 signals. So we have the HA, that's a methyl group. They're all equivalent to each other. Here we have the HB. This is a CH2 group, but I don't see any chirality centers anywhere, so they're equivalent to each other. Here we see the HC. Again, it's a CH2 group. None of the, there's no chirality centers. They will be equivalent to each other. Here we have an HD, right? And here's a methyl group. These 3 protons are all equivalent to each other. And here's another methyl group. These 3 protons are all equivalent to each other, but because of a rapid mechanism, not symmetry, a rapid mechanism, this bond is rotating billions of times per second at room temperature. And so this methyl group becomes this one, and this methyl group becomes this one, right? It's not symmetry. The molecule isn't frozen in this shape. This methyl group is spinning up here, and this methyl group is spinning down there. So they are exchanged by the rapid mechanism, just like the axial protons and the equatorial protons in chair cyclohexane are exchanged by a rapid mechanism. So all 6 of these protons are all equivalent to each other, not by symmetry, but by a rapid mechanism. So I'm calling these all the HE. So there are 5 signals. Okay, so next, let's talk about the splitting pattern. Okay, the HA. What will be the splitting pattern of the HA? I need a word that ends in "et." Splitting pattern of HA is a singlet, right? Because the HA, we're looking for 2 bond splitting and 3 bond splitting. The HA are 2 bonds away from other HA protons. There is no splitting between equivalent protons, and there is not another proton 3 bonds away, so that's going to be a singlet. What about the splitting pattern of the HB? What's its splitting going to be? I want a word that ends in "et." Can I explain the singlet again? So we're looking for 2 bond splitting and 3 bond splitting. The HA is 2 bonds away from another HA proton. There is no splitting between protons that are equivalent to each other. So is there a proton 3 bonds away from HA? 1, 2, 3. Nope, that's an oxygen. 1, 2, 3. Nope, that's a carbon. So what's the splitting pattern of HB? A triplet. What's the splitting pattern of HC? Splitting pattern of HC is going to be another triplet. Okay, what's the splitting pattern of the HE? Oh, okay, now this is a hard one, right? This is a hard one. The splitting pattern of the HE, that's a doublet, right? Because every HE proton is 2 bonds away from another HE proton, no splitting. But every HE proton is 3 bonds away from 1 HD proton. N equals 1. 1 plus 1 is 2. It's a doublet. Okay, what about the splitting pattern of the HD? Oh, that's going to be a septet. Because the HD protons are three bonds away from 6 HE protons. And all those HE protons are all equivalent to each other. Okay, so I'm going to call this guy A. Oh, I already did that, sorry. Okay, so now it's time to sketch the NMR and see what the spectrum is going to look like. Now, here you're at a great disadvantage unless you've memorized the NMR chemical shifts. So you don't need to memorize any NMR chemical shifts. You can always look at a table. You can look at a table, but you know what? I've memorized all of these NMR chemical shifts, so I never need to look at a table. But say we're trying to sketch the spectrum, we'll just I'll just give you some guidance here. But for a quiz, an exam, or something like that, and a problem like this on quiz 4, 100% guaranteed, right? You're going to have to refer to a table, right? And I'll give you the table that I want you to use. But before such time, we can just come up with some. We can just come up with the sketch based on just general principles. All right, so this is very messy here. So let me just rewrite this. And let me ask you some questions about this. What do you think is going to be the most upfield over here? What's going to be the most upfield signal? Is it going to be the HA, the HB, the HC, the HD, or the HE? Tell me in the chat. What are you thinking of for the most upfield signal? Farthest away from an electronegative atom and farthest away from a multiple bond. What do you think is going to be the most upfield signal? The A, B, C, D, or the E? Oh, it's going to be the HE is going to be the most upfield signal. Because see, the HE is 1, 2, 3 bonds away from oxygen, right? The HD, 2 bonds away from oxygen, so that's going to be downfield. The HC, 2 bonds away from oxygen, that's going to be downfield. The HB is 1, 2, 3 bonds away from oxygen, but also close to a double bond, right? The HA are 3 bonds away from oxygen, just like the HE are, but the HA are close to this multiple bond, those pi electrons. And remember when we were talking about the trends in the NMR chemical shift, we said it's not just electronegativity, it's also how close is the observed proton to a pi bond. So the HE are farthest away from electronegative atoms and farthest away from the multiple bond. That's going to be the most upfield signal. So it's going to be a doublet. And I have memorized all of these chemical shifts. You would be looking at a table. And so that table is going to say the ppm of this doublet is going to be about 1 ppm. I'll explain that table later, how to use that table later, but just for now, I'm just trying to develop a feeling for the chemical shift. So I'm going to put that doublet, and that doublet is 6 hydrogens. It's going to be huge. It's going to be a huge, huge doublet here at about 1 ppm. It's a 6 hydrogen doublet, right? That's going to be the HE. Who's going to be the most downfield this way? Who's closest to electronegative atom, and who's closest to the pi bond? Is it going to be the HA, the HB, the HC? Who's going to be closest to who's going to be the most downfield? The most downfield over here. Most downfield signal is going to be the HC, because the HC are 2 bonds away from oxygen. No, the only other proton that can say that is the HD proton. The HA is 3 bonds away from oxygen. The HB is 3 bonds away from oxygen. So the HC proton is 2 bonds away from oxygen, but the HC are closer to this second oxygen and closer to this multiple bond, to this double bond. So the most downfield signal is going to be the HC, and that's going to be a triplet. And where is that triplet going to be? Somewhere in the 4s. I'll explain how to use that table later. Right now, I'm just trying to get a feeling for who is going to be most upfield and who's going to be most downfield. So over here, we're going to have a triplet, and that's a 2 hydrogen signal. So this signal is not going to be as big as this one, because this is caused by 6 hydrogens, this one only by 2 hydrogens. What's a triplet look like? A triplet looks like a 1 to 2 to 1 affair, like that. So this is a 2 hydrogen triplet due to the HC, the most downfield. What if I were to tell you that right next to this triplet, there's going to be another signal? Who's going to be the second most downfield signal? Right, we've taken care of the E and the C. Who's going to be right up against, very close in chemical shift to this triplet? Oh, that's going to be the HD septet, right? Because the HC and the HD, they are both 2 bonds away from that electronegative oxygen, but the HD is farther away from the second oxygen than HC is, and the HD is farther away from that multiple bond. So we're going to have a 1 hydrogen septet very close in chemical shift to this guy. All right, so what does a septet look like? Well, you know, I've memorized many things, but I have not memorized that. So it's the septet, let's see, quintet. The septet is going to be a 1 to 6 to 15 to 20 to 15 to 6 to 1. right? A septet, but the center line is going to be much, much bigger than the outer lines. In fact, you may not even be able to see the outer lines. And it's only caused by one hydrogen, so it's going to be small. So I'm going to put this right here. I'm going to put this right here, and this is not going to be the scale, but it's going to be what? 6, 15, 20, 15, 6, 1, something like that. But it's going to be very small, right? This is a one hydrogen signal. It's small because only one hydrogen is making that. Okay, so that's the that's the HD. So we've taken care of E, we've taken care of D, we've taken care of C, and now A and B. So tell me about A and B. Who is more upfield and who is more downfield? Is it going to be the A? Is the A going to be upfield and the D and the B downfield? Or is the B going to be upfield and the A downfield? So who's most upfield? Who's most upfield over here? The HA or the HB? Yeah, it's going to be the HA, because the HA and the HB are equally far away from this oxygen. They are equally far away from that multiple bond, but the HB are closer to the second oxygen. So it's going to be an upfield HA at around 2 ppm. And it's going to be this big, huge, majestic singlet caused by 3 hydrogens. That's the 3 hydrogens of the HA. And downfield from that is going to be the triplet due to the HB. And so I'm going to put that over here somewhere. And a triplet is a 1 to 2 to 1. And so that's our 2 hydrogen HB. All right, so there's the sketch of our spectrum. All right, so now let's look at the actual spectrum and see how we did. Okay, so memorize this, right? Memorize this. Triplet, septet, triplet, singlet, doublet. So I think I have the actual spectrum here somewhere. Hope so. Where is it? Yeah, there. Yeah, there it is. Oh, we did damn good. Triplet, septet, triplet, singlet, and doublet. All right. And so notice that the size of these peaks is correlated to the number of hydrogens that are producing each signal. This septet is very small compared to the other signals. And what I did here in the spectrum is I have a blow up of these 2 signals here. And we see that this septet, which was a 1 to 6 to 15 to 20 to 15 to 6 to 1, these outermost lines, they're tiny. You can hardly even see them unless you have a blow up. Okay, so more of this tomorrow, where we have that shortened lecture and then we have the quiz. So we'll continue talking about sketching NMR spectra tomorrow, and we'll see how to use the table for the